and welcome to this session on sine bar and its applications. Let us begin with the session.
Let us look at the objectives of this session. At the end of this session, you will be able to state the features of sine bars, specify the sizes of sine bars, state the principle of sine bars, state the different applications of sine bars. A sine bar is a precision measuring instrument which is used along with the slip gauge blocks for precise angular measurement. It is an accurately finished rectangular bar made of corrosion-resistant, stabilized high chromium steel. It consists of two precision rollers of the same diameter on either end of the bar. The axes of the rollers and also the line joining these axes are parallel to the top face of the sine bar. The top face of the sine bar is parallel to the surface table when both the rollers are rested flat on its surface. The distance between the axes or centers of rollers is fixed to a high degree of accuracy. The size of the sine bar is specified by the distance between the centers of the rollers. The commonly available sizes are 100 mm, 200 mm, 250 mm, and 500 mm. Sine bars are also provided with drilled holes along its length to reduce the weight of the sine bar and also to facilitate clamping. The principle of a sine bar is based on the trigonometrical function. In a right-angled triangle, the sine function of the angle theta is equal to the opposite side of the angle by hypotenuse. The cosine function of the angle theta is the adjacent side of the angle by hypotenuse. The tangent function of the angle theta is the opposite side by the adjacent side of the angle. Let us learn about slip gauges. Slip gauges are used for setting the sine bar to different angles or while measuring unknown angles using sine bar. A surface table provides the datum surface for the setup when sine bar is placed over the slip gauge set. If one roller of the sine bar is placed on the surface table and the other on the slip gauge set, the structure formed by the sine bar, surface table and slip gauge set forms a right-angled triangle as shown. The sine bar forms the hypotenuse C. The stacked slip gauge height A forms the opposite side to the angle theta, and the distance B on the surface table forms the adjacent side to the angle theta. The sine of the angle theta is opposite side by hypotenuse. Therefore, sine theta is equal to A by C. The hypotenuse C, distance between the rollers, is constant for a specified sine bar. For example, for a sine bar of size 100 mm, the hypotenuse C shall always be 100 mm. By stacking the slip gauges to a calculated height A, one can set the sine bar to a required angle theta. For example, to set the sine bar of size 100 mm to an angle of 36.87 degree, we need to stack the slip gauges to a height of 60 mm. By knowing the slip gauge stack height A set for a specified sine bar size, one can also determine the angle theta. For example, by stacking the slip gauges to a height of 70.71 mm for a sine bar of size 100 mm, we can obtain an angle of 45 degrees. The advantages of sine bars are: it is precise and accurate, its design is quite simple, it is easily available. The disadvantages of sine bar are: it is an indirect method of measurement, hence any differences in the surface results in inaccurate measurement of angles. Inaccuracy increases with increase in angle. The previously discussed procedure is not suitable to measure or set angles above 45 degrees. Handling and fixing positions may create problems. The applications of sine bar involve measurement of angles accurately, face and locate any work to a given angle for machining operations like milling, grinding, etc. Face and locate any work to a given angle for inspection or marking applications.
To recap, we have learned to state the features of sine bars, specify the sizes of sine bar, state the principle of sine bars, state the different applications of sine bars. So that's all about sine bar and its applications. Hope you have understood all the concepts. See you in the next session.